Welcome to my channel. In this video we will learn about the Master's Theorem or Master's method. So which is normally used in the algorithm analysis in order to find out the time complexity of a particular algorithm from a recurrence relation. So in the last videos we have seen about the substitution method and recursion tree method. So this is like the master method is like a cookbook method. That means it provides direct formulas for the particular recurrence relation. So we can easily solve the recurrence relation here. So in order to solve the recurrence relation and to find out the time complexity of a particular relation, so it must be in this format: t of n equals to a into t of n by b plus f of n. So here the a value must be greater than or equals to 1, b must be greater than 1, and f of n must be always positive. So these are the three cases given for the Master's theorem, that is f of n equals to big O of n power log a base b minus epsilon for some epsilon greater than 0. Then t of n equals to theta of n power log a base b. So this condition will apply. So if the f of n equals to big O of n power log a base b minus epsilon. If suppose f of n equals to theta of n power log a base b. Okay. So then t of n equals to theta of n power log a base b and log n base 2. If f of n equals to omega of n power log a base b plus epsilon for some epsilon greater than 0, and if a into f of n by b is less than or equals to c into f of n for some constant c less than 1 and all sufficiently large n, then t of n equals to theta of f of n. So this is the direct formulas given for the Master's theorem. So you can find these formulas in any textbook. So these are directly given. So if you want the simplest form for this formula, so we can go with this one. Actually I searched in the net for this one. So this is very simple compared to this one. So we may get doubt that how these formulas are obtained, right? So here they have mentioned the big O, theta and omega, but here they have not mentioned any big O or theta or omega. How is it possible to get these formulas? So does it really work or not? So yes, these formulas are correct, because so if you observe for the big O notation, so big O is the upper bound of the runtime of the algorithm, and big O is the worst case of the algorithm. So this is the worst case of the algorithm. So that means f of n is less than or equals to, so for the big of n, so f of n is less than or equal to c into g of n, right? Okay, so we are including this same thing here by excluding the big O. So actually we are mentioning the big O here. Less means f of n less than c into g of n, right? Okay, c is the constant, so this is z of n. So f of n is less than g of n. So that means big O notation. So next, this one is same as it is written here, second case. And third case, f of n equals to omega of n power log a plus epsilon base b. So we know that omega is the best case, right? So it is the best case of the algorithm, or it is the lower bound of the runtime of the algorithm. So which is mentioned as f of n greater than or equals to c into g of n. So this is not less than or equals to less than c into g of n. So greater than or equals to c into g of n. Then this formula will apply. So f of n, so c is the constant here, g of n is n power log a base b. So t of n equals to theta into f of n. So if this condition occurs, then we must it will result in the t of n equals to this type of time complexity. So now we will know clearly about this using an example. So given the recurrence relation, T of n equals to 2 into T of n by 2 plus n. So here, so based on the given formula, so A equals to 2 and B equals to 2. So A is 2 and B is 2. So we get A equals to 2 and B equals to 2 and f of n equals to n, right? So first of all, we need to find out the n power log a base b. So here given, right, n power log a base b, we need to find this one. So n power log a is 2, b is 2. So that means 1, that equals to n. Okay. So this is the n power log a base b value is n. So we need to compare this with the f of n. Okay. So f of n is equals to n, right? So f of n is equals to n power log a base b. So this is n. So these two are satisfying. So these two are equal. So now the case 2 is satisfied here. So we'll consider the case 2. Okay. So case 2 is, so T of n equals to, so if this condition satisfies, then we will go to this relation, right? So T of n equals to theta of, so n power log a base b is n into log n. So theta of n log n. Okay. So this is how we can solve the recurrence relation very easily, and it is like a cookbook. So we can directly obtain the formulas from the, we can directly write the time complexity, so by using the formulas simply. So we need to remember this formulas here, these 3 cases. Okay. And there are some limitations for the Master's theorem. So we can apply the Master's theorem for only certain type of recurrence relations. So we cannot apply this type of the relations for Master's theorem, like if suppose T of n is not monotone. That means T of n is not monotone. That means, so we cannot apply the Master's theorem if it is in the format of trigonometric relations, that is sine, cosine, like that. Okay. So we can't use the Master's theorem for this type of relations. So next, f of n is not polynomial. So the f of n value should not be polynomial. So f of n is 2 power n also won't work. So for this type of relations also, Master's theorem won't work. Next, a should not be a constant. A is not a constant. Okay. So then if it is in this format also, the Master's theorem won't work. So this is all about the Master's theorem, the limitations of the Master's theorem, and how we can apply the Master's theorem. Hope you like the video. Thanks for watching my video.